Hi everyone, I'm back with the third session on sound. We were discussing about sound and the wave propagation. We looked at the characteristics of wave, which is the amplitude, the period, the frequency, and all that. We're going to discuss on the same point a little more detail in this session, and then we'll also go ahead with a few other points on whether the sound requires medium of propagation, right, and also how does a human ear work and so on. So we will look at some of these portions today. Now let me just let you know that this presentation is coming from, this video is coming from Navayug study at gmail. It's coming from a study channel called Navayug study. If you want to get in touch with us, you can use the email ID navayug.study@gmail.com, and if you have any questions, suggestions, feedback, you please do send emails to us on navayug.study@gmail.com. And we also have a website, navayugstudy.wordpress.com, where you will get all the links and all the links to all these videos, links to the presentations and all that I'm using, notes and so on, in navayugstudy.wordpress.com. It also has ways of submitting questions. If you want to ask for a one-on-one video class with me, you can request that. It doesn't happen immediately. I will schedule it based on my availability. I am actually a professional employed elsewhere, and so usually typically I get times on the weekends where I can actually schedule the one-on-one session whenever that's possible. So let me continue with where we left last session, and that was, we discussed about ultrasound, right, and how the ultrasound can be used. And we looked at ultrasound being used in ultrasound scanners, ultrasound being used for homogenization, ultrasound being used for detection of cracks when there are welding and so on done in mechanical engineering. And we saw all these various different ways the ultrasound can be used. We also looked at the characteristics of a sound wave. I would like to go back to that specific discussion about characteristics of sound wave and want to go in a little more detail into what really is a sound wave. We discussed about the sound wave in the last session, and we told that it's a longitudinal wave, right? Now look at this. Now what is happening is that you have a vibrating surface. It could be the diaphragm of a drum, or it could be a table. When you hit the table, it vibrates. It could be a string of a guitar, whatever. So assume that this is string of a guitar, right? So this is string of a guitar. Remember, I showed you a video of a slow motion of a string and you saw that the string vibrates, and it is that vibration of the string which is producing sound. Now how is the sound being propagated? How that vibration which the guitar string has reaches your ear? That's how you are able to hear the sound of the guitar. Now how is it happening? And that is what in fact this diagram is explaining. I did explain this to an extent last time, but I want to explain that again. Look at what is happening in one single movement. When the string is moving this way, it is compressing air. It is compressing air, and that is why you have a compressed region. Now this is a moving thing, but let us look at, if I stop, let me stop this now for a while, and let us see how it looks like. So I stop it, right? Sorry, I'm not able to see it when I stop it. Okay, when I stop it, if I take a snapshot at a particular point, it looks like this, right? So you have certain areas with high compression, that is higher pressure than the atmospheric pressure. So you can see these areas. These are all high pressure areas. Tell me. That is for example string of a guitar. Yeah, correct. It could be string instrument. It could be a diaphragm of a drum. Remember I showed you somebody drumming and you saw the way how the cymbal was bending and vibrating, right? How the diaphragm of a kettle drum in a jazz, right? A set of drums was vibrating. So even it could be that. So it could be any vibrating object or a body which is producing the sound. Now when it vibrates, what it's really doing is that at the point when it is vibrating, so it is again oscillating, right? So in fact, you look at this, this is oscillating. And while it is oscillating, when it is moving this way, it is compressing air, right? It is pushing the air. Have you tried doing this? When you try doing this, you can feel that you're pressing the air, you're compressing the air. When you're moving it this way, at that point, you see the air around is coming here. Why? Because when you're moving this way, at that point, you're reducing the pressure. You're pushing the air out. Whereas when you're doing this, you're pressing the air. So what is happening is when it is moving this way, it is compressing the air. When it's moving this way, it is reducing it is pushing out the air. It is pushing out the air, because of which there's a low pressure area being created. So you have an alternate high pressure area and low pressure area. High pressure area, low pressure area. And so what is happening now? When it is creating, so it has created a high pressure area. Now you can see that high pressure area is moving. It is moving in this direction. You can see the high pressure area is moving, and also together with the low pressure area is also moving, right? So you have high pressure area and low pressure area. Look at this. So you have a high pressure. Now if I had stopped this and taken a snapshot, this is how it will look. So you have alternate high pressure and low pressure areas. Right?
Yeah.
And how is this high pressure area moving? How is it moving away from the string? The reason is because now what happens is that when this high pressure area is created, that high pressure area pushes the air nearby it. And so now that becomes a high pressure area. Then that pushes the air nearby it again. Then that becomes high pressure area. And so that way the high pressure area is transmitted, right? So the high pressure, so what is happening is the high pressure and low pressure regions are transmitted. So the high pressure and low pressure regions are transmitted in the direction of the sound, right? That is basically what is going on. So it is getting transmitted in the direction of the sound, and that is what you see here. So the wave is moving. But are the air particles, the air molecules moving? No, they are not. You can see that. You look at any particle here. Let us take any particle here. What is happening to that particle? That particle is not moving away. It is just oscillating in that mean position. That's all what is happening. You can see that particle is not moving. It is just oscillating. So none the
No, where when the string is vibrating and the high pressure area is moving along, in the end of that place there is one place just oscillating around. And all the particles are just oscillating.
Yeah, all the particles in air, all the molecules, all the air molecules are just oscillating. They are not moving. So it is not that the particle here after some time reaches here. It doesn't happen, right? So the particles in the medium are not moving. What is happening? They are just oscillating. They are just oscillating. Right? So the particles in the medium are not moving, they are just oscillating. So these are some of the very important inferences that you can draw, and this is what is called a longitudinal wave. Why it's a longitudinal wave? As I explained in the last session. Why I'm explaining again is some of the students really didn't get this concept clearly, so that's why I'm repeating. So why is it called a longitudinal wave is because the oscillation, the direction of oscillation of the molecules in the medium or the particles in the medium is in the direction of transmission of the wave, right? So you look at this, now you can see this particle is, so the particle in the medium is vibrating, oscillating this way.
So
And what is,
so when the high pressure area is moving that way, then those low pressure particles will also be oscillating the same direction.
yes, so that's right. So they are oscillating, and we have got alternate high pressure and low pressure regions which is being transmitted, right? And if you look at the direction of oscillation of the the particle, the air particle, or whatever medium it may be, it could be water particle or a water molecule or air molecule, based on what medium it is, right? The direction of oscillation is exactly same as the direction of transmission of the wave. So direction of transmission of wave is this, right? The direction of transmission of wave is this, and the direction of oscillation is the same as the direction of transmission of the wave. So that is the key point here, and that is why it is called a longitudinal wave, right? Whereas if you look at a transverse wave, so is this clear?
Yeah.
Very clear?
Yeah.
Yeah. So I am just raising this. Now let us look at the transverse waves. So this is an example of a transverse wave. Actually, even in the case of transverse wave, what is happening is, yeah, they're oscillating, but
Oscillating, but not horizontally. They're oscillating vertically.
yeah. So here the wave is transmitted. The wave is transmitted in this direction, but the particles are oscillating perpendicular, in a perpendicular direction to the direction of the wave. That is why it's called a transverse wave.
Like the water.
Yes, the surface of water is transverse wave, absolutely, right? So this is longitudinal wave, and it is a mechanical wave. Why is it called a mechanical wave? It's a mechanical wave because it is really because of the movement of the particles. So that's why it's called a mechanical. It's also called a mechanical wave. And what is the example? One of the examples of a longitudinal wave? Sound. Sound is an example of a longitudinal wave, right? So sound is transmitted as a longitudinal wave, whereas here this is a transverse wave. I hope this is clear. The concepts are clear. All right. Now I want to also explain about how do you represent the sound wave graphically, right? How do you represent the sound wave graphically? For that, I want to actually go here, right? Now let us look at this wave. So this is a longitudinal wave, and I can actually draw a graph, right? So I can draw a graph. I'll use a different color for that, maybe red, right? So this is a graph I am drawing, and on this axis is time, and on this axis is pressure. So now what is happening? Now assume that this represents the atmospheric pressure, right? So this is atmospheric pressure. So let us look at what is happening here, right? So let us look at here. So this is a high pressure area. This is again a high pressure area. This is again a high pressure area, right? So what is really happening? And this is a low pressure area. So here the pressure is low. Let me change the color. So here is the pressure is low. Okay. So here the pressure is low, right? Now let me take. And here the pressure is high, right? And then here the pressure is low. Oops. And here the pressure is high, and so on, right? So you have a wave kind of representation.
And even musical sounds also have this kind of
Yes, music, any sound is going to be longitudinal wave. So what will happen? The pressure variation will be like this.
But in case of a noise, it is not doing the same.
Yeah, so now that is where what you call a note, right? So we'll discuss that later, right? We'll discuss about sound, I mean, music and noise later on, right? We'll discuss that later. So if you look at this, this is the way it is. So if you look at, I don't think I've drawn it well, right? I can draw it a little more better, probably. Just try to draw it a little more better. So, oops. So this is what they call the ambient pressure, right? This is the ambient pressure. Typically in the case of atmosphere, it is atmospheric pressure, right? Huh?
Those dots over there.
No, not dots. I mean, that dot is representing the ambient pressure on the x-axis, the y-axis.
Those dots are the ambient pressure.
Yes, that is showing that is representing the. I am drawing a graph, right? So I need not explain about the graph, right? You know about graphs, don't you? I should erase this. Sorry, I'm again redrawing it because this so.
So this is longitude.
No, wait. Let me explain this. And then I will draw one line here which represents the what you call the ambient pressure. So this represents the ambient pressure, right? Now, how is the pressure going to vary? So if you look at this, so pressure is going to vary like that, right? So low pressure here, and then pressure increases, goes down, then again there is a low pressure here, again goes up, again goes down, again goes up, like that, right? So that's how the graph is going to be. So you have a low pressure area, then a high pressure area, and low pressure area, high pressure area, low pressure area, high pressure area. So this is what we call a peak. Not a good color. This is what we call a peak, and this is what we call a trough, right? So if you look at a wave, right, if you look at a wave here, how does a wave? So you have a low pressure area, then a high pressure area, and a low pressure area, and then so this is representing a wave. So if you look at here, you have a low pressure area, and then a high pressure area, and then a low pressure area. So that is representing one single wave, right? So if you look at it, it is repeating. So low pressure area, then a high pressure area, then a low pressure area, a high pressure area. So it's repeating. So one wave is basically it's a cycle, one cycle, right? So if you look at here, you can say this is one wave, right? Starts here, go through a low pressure area, rarefication, then a compression, and back after that. So we started at ambient pressure, then there is a rarefication because the string has moved this way, right? Then the string is going that way, then it is compressing, and then it is coming back to the mean position. So string is at a mean position. So when the string is at the mean position, there is no pressure variation. because it's not moved yet, right? Then it is moving this way. So what happens? Now it is moving this way, means the pressure is reducing. So it is creating what you call a rarefaction.
So it's a
This area is called a rarefaction. 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 And this, as I told you, is compression, right? This is what you call compression. Compression. So what is happening? You are in the mean position first. The string is in the mean position. It is moving this way. Then that leads to a rarefaction, because when it moves this way, the pressure in this area slightly reduces, right? Then the string is moving this way. Then it's compressing the air around, so it creates a compression. Then it moves back to the mean position, right? So where the pressure comes back. So when it is in the mean position, the pressure of the air around is atmospheric pressure. Then when it moves this way, at that point, the pressure is slightly reduced than the atmosphere. Slightly, not a lot, slightly reduced. Then when it moves this way, it compresses air, so the pressure increases a little more than atmospheric pressure. Then it comes back to mean position, again the pressure comes back to atmospheric pressure. So that whole thing, that whole cycle is one wave.
So where's the compression here? Where you mark compression?
Compression is, this is the compression, right?
So that
So corresponding to that, there is a peak. The pressure is higher here. See?
so that vertical line
That is just showing, I just see, I've taken one longitudinal wave and I'm showing the corresponding pressure variation in a graph, right? So at this position, what is happening? There is a high pressure area. So here the pressure is increasing. Then there is a low pressure area, which is rarefaction. So the pressure is reducing. So that is what I'm trying to show. So here again is a low pressure area, so the pressure is reducing. So it's a trough, and there's the lowest, and here is where the lowest pressure happens. And I'm just saying how that is happening, right? So you had the mean position, the pressure around is atmospheric pressure. Then the string is moving this way. When the string is moving this way, at that point, it is pushing out air from there, and so because of that, the pressure in that area reduces a little. So it creates a rarefaction. Then the string is moving this way. At that point, it is pressing the air around, and so that it is producing a compression, compressed region. Then it is moving back to the mean position. So then what is happening? Pressure again reduces back to the atmospheric pressure. And so this is a cycle which is going on. Then again it is moving this way, right? It reaches mean position, again it moves this way, again rarefaction, then it compresses, then it comes back to the mean position and again goes. So compression, rarefaction, compression, rarefaction, compression.
So that if it moves this way, it is kind of a longitudinal.
Yeah, it is a long. I am explaining about longitudinal waves only, no? This is a longitudinal wave, right? So what I am explaining about is longitudinal waves. This is a longitudinal wave, and I am talking about the pressure variation within that wave, right? And I have plotted it using a graph, right? I have plotted it using a graph. So now you can see that there is a low pressure area and there is a high pressure area. Then there is a low pressure area, there is a high pressure area. There is a low pressure area, and there is a high pressure area. So that is basically. Yeah, so in fact the pressure wave is looking like a transverse wave, right? But really we are representing, it's a longitudinal wave. The pressure graph looks like a transverse wave, right? But the wave itself is longitudinal. Okay, is that clear? Okay. Now if I take a graph like this, so I hope that this is clear, right? Any questions on this?
No.
Okay, fine. So shall I clear this now? Okay. So now let us go here and let me draw a graph now properly. So now and let me mark, so this is the time and this is pressure, and this is in typical case this is atmospheric pressure. You should stop using this pad, you should start writing in book. I am seeing sheets here and there everywhere. so you'll start losing atmospheric pressure. So, or you can say ambient. If it is water, it's the pressure in the water, right? So this is basically what you call the ambient pressure. And as I told you how the pressure is varying, right? So if I draw the pressure variation, so it's going like that. So it goes like that and then goes like that. Then again comes down like that and then goes up like that. Right? So this is how it is. And if you look at one single wave, what is one single wave? So one single wave is this. It starts from here, right? So this is one single wave. So this is what is one single wave is. So you have a rarefaction area, and then so you have a rarefaction, then you have a compression, and then back to. So you are starting when the string is in the mean position, we are here. Then the pressure as the string moves this way towards left, let us assume. Then the pressure is reducing. Then when it is moving back towards right, the pressure is increasing, and then it's coming down. So this is one wave, right? Now, so using this wave, I can now explain all the properties, right? So if you look at this wave, this time, right? This time that is nothing but a, what is that time? What is this time? This time is one of the properties of the wave. What is the property of the wave? Which time period precisely? So this is the time period, right? I'll call it T, right? So this is a time period. Okay, and it's not actually, this is not time. I'm sorry, made a mistake. Yeah, this is actually space. Sorry, there's a small mistake which I have done. This is not time. This is also not time. This is in fact displacement, right, or distance. So if you look at if you go back and
That is the displacement, then what about that? Black line is also displacement.
see, if you look at here, right, see, this is the displacement, right? So here is where the string is, and at this distance you have a compression, at this distance there's a rarefaction, at this distance there's a compression. So in the space the wave is moving, right? And we are talking about the distance from the source, right? So that's basically what it is. So I made a mistake, I'm sorry for that. So
If that
so
is also x, then that black line is also x.
this is also x, and this is the length of a wave. This is the length of a wave. One wave, what's the length of it? So if you go back and see here, right? This is the length of a wave. This is the length of a wave. I hope you're concentrating. So so this is the length of a wave from one rarefaction to the other. So from one ambient point to the other ambient point. So that's actually a length of a wave, right? So similarly here, this graph is also showing a length of a wave. So this is the length of a wave, and that is what is called a wavelength. Wave length.
So that's also x only. That black line.
Yeah, so x, basically what is x? It is actually the distance, right? So distance from the source.
That's the distance of the wave.
Distance of various points in the wave, right? distance of various points in the wave. So you have a point which is in the ambient pressure, then you have a point which is at the lowest pressure, there's a point which is at the highest pressure, right? And this is one complete wave, and the total length of one wave is called a wavelength. The length of one wave is called a wavelength, right? Now assume let me finish this wave also. So assume that in 1 second the number of waves produced is this much, right? So assume that it is producing 2 waves in 1 second, right? So there's one wave, then there's another wave, right? So there are 2 waves being produced. You should understand, even though you're looking like this, physically the mechanical waves, compression and rarefaction. We are just looking at how the pressure variation is, and using this particular graph we are representing that longitudinal wave because it's easy to visualize, right? That's the reason. So now you're saying that this particular string, the guitar string, it is vibrating in such a way that it is producing 2 waves every second, right? So it's producing 2 waves, which means its frequency is
it is
2. Yeah. So in which case, if it is producing 2 waves in a second, means it definitely the source would have vibrated 2 times, oscillated 2 times, right? Which means the frequency is 2. What's the unit?
2
Hertz. 2 hertz, right? So the unit is 2 hertz. So its frequency is 2 because it's producing 2 waves every second. You have seen that the length of one wave is called a wavelength, and this is the amplitude, right? The maximum pressure is basically the amplitude, right? So this is the amplitude. So we've seen the wavelength, the amplitude, and we have the frequency. So these are the 3 characteristics of a wave, right? The amplitude, wavelength, and the frequency. I hope this is clear. And then we have the
you have written L there.
what?
You have written L over there.
Where?
Near that vertical thing there.
Here.
Yeah.
This one. This is just an arrow saying this is an amplitude. This is amplitude. So amplitude, wavelength, and the frequency, right? So I think we have got all these idea and we have understood. So always, when you see diagrams of representing wave, they will straight away show a pressure chart. You will wonder, what is this? You're talking about longitudinal waves and you're showing some transverse wave. What is this? In fact, it is showing the variation of the pressure because of the longitudinal wave, right? I hope that is clear. Is this clear? The graph representation of pressure?
Yeah.
Clear. And we've seen wavelength, amplitude, period, right?
Ambient pressure.
Ambient pressure, yeah. So ambient pressure is basically that. Typically, if you look at in current in this room, the ambient pressure is the atmospheric pressure. If you look talking about down in the sea, the ambient pressure is the pressure of the water there, right? So basically, the pressure of the pressure of the medium.
And even in air, it is the pressure of air.
Pressure of air is what? Here, what is the pressure of air? Atmospheric pressure, right? So that's basically what it is. So I hope that's clear, right? And so all these things is happening when I'm talking. In fact, my vocal cord is vibrating inside, and due to the vibration, it is creating small low pressure, high pressure, low pressure, high pressure areas, and that is transmitted through the medium, and that is basically the longitudinal wave. All right, clear? Okay, let me just all right, so now let us go back to So I know that it was a long explanation, but I think I wanted you to get the real idea of longitudinal waves and how does it really work and what does that pressure chart typically everybody shows. What does really that mean, right? And I hope that's clear. Now let us go back and continue with the presentation, right? So now that we are very clear about what is a longitudinal, how the sound waves are transmitted, they're transmitted as a longitudinal wave, and we've seen the characteristics of the wave, which is the amplitude, the wavelength, the frequency, and all that stuff.
The ambient pressure.
Yeah, the ambient pressure is just the pressure of the medium, right? So we have seen what is the variation of pressure which is produced because of the longitudinal wave.
We
So
also found the peak and trough.
correct. So if you look at every wave, it will have a peak, it will have a trough, right? The lower pressure area and a higher pressure area, right? So that's basically what it is based on the movement of the source. So that's basically what the sound means. Now, if you look at the transmission of sound, right? The speed of the sound, how it gets transmitted, it is not same everywhere. If you look at the speed of light is a constant, right? It doesn't matter whether it is coming through air, whether it's coming through water,
It has the same.
it has got the same speed. The reason is because the sound is not a mechanical wave.
That is why we see the light, the flash.
No, yeah, I am not that is different thing. That's because the speed of light is higher. But what I'm saying is, if you look at the speed of sound is different in a solid, in a liquid, and in a gas. See, you can see here, right? So, if you look at the speed of sound, now let us look at a train, right? Now, assume the train is far away. It takes a lot of time for the sound of the train to come through the air and reach your ear. But assume you keep your ear on the rail. You'll get that sound far more faster. Because the sound is also getting transmitted through the rail, it is also getting transmitted through the air, and the speed of sound on the rail is far higher. You can see that, right?
That's in case solids.
Rail is a solid, no, it's steel,
Yeah.
right? So you can see that the speed of sound is very high in solids. It is lesser in liquids like water,
In middle order.
but if you look at air, it is the least, right? So you can see, and why this difference is because the sound is a mechanical wave. Sound is a mechanical wave.
There's nothing but a longitudinal wave.
Yeah, sound is a longitudinal wave, Sidhu. It's also a mechanical wave because it requires a medium for transmission, and it's because of the vibration of the particles in the medium the sound is transmitted.
Yeah,
Right?
but you also said another name for longitudinal wave is mechanical.
No, not necessarily. A transverse wave can also be a mechanical wave. So it is not that all mechanical waves are longitudinal. No. If you look at a water surface moving, that is also a mechanical wave. Because it is because of the particles, water molecules which is vibrating, that waves is produced. Right? So even the transverse wave is also mechanical waves are waves which needs a medium, and the transmission of the wave happens because of the oscillation of the particles inside the medium. So it could be a transverse wave, it could be a longitudinal wave. So what I'm saying is, since sound is a mechanical wave, it is a longitudinal wave, it is also a mechanical wave. Because of that, the type of the medium, whether it's solid or water or liquid or gas, based on that, the speed of transmission changes. Right? So why I'm trying to explain why there's a difference in speed of sound between solid, liquid, and gas. The reason why there's a difference is because sound is a mechanical wave, and the sound is getting transmitted because of the vibration of the particles inside the medium. And if you look at the solids, the particles are very thickly packed. So the transmission is far more faster. Water or liquids, the liquids are a little more loose, the molecules are more apart. So transmissions is not as fast as solid. But if you look at air, it is absolutely loosely packed, right? Yes. So that is the reason why the transmission of the speed is different. I hope that's clear. Whereas if you look at light, light is not a mechanical wave. It's an electromagnetic wave, right? We'll discuss that later, right? And we'll try to understand what that means later on, maybe in 11th standard or something. We'll discuss that to that level. We'll discuss about dual characteristics of light, and it's very interesting, right? So I hope this is clear, right? So, and we have understood why the speed is different, because the sound is a mechanical wave, and so the way the particles are packed in the medium matters a lot in terms of what's the speed in which the sound gets transmitted in that medium. And that is why in solid it's far more faster than in the case of a gas. All right. So I hope that's clear, right? Now, if you look at, some people think that, it does really sound, travel in water. I mean, can people hear inside? Yes, definitely yes. Because how do whales communicate? Right? The whales communicate through sound, but the sound that they produce are ultrasonic sound, so we cannot hear them, right? But the waves do communicate. Now, I am actually trying to show you one simple example of a recording. Now, this recording is done by using a special recorder, right, which can record ultrasound. So let me increase the volume. Oops, what did I do? Sorry for that. So let me just play this. I don't think it's playing due to some reason. It's not playing. Okay, I think I will not wait for that to play because it does seem to have some problem, the player. So you can try it out yourself. In fact, you can see some sounds being produced by the humpback whales. They are in fact ultrasonic sound, but they have recorded it using some special recorder. And the scientists are finding that the whales even have some kind of a language, right, to communicate with each other. And they use echolocation, plus they also have some ways of communicating with the other. Whales also have the notion of a family, right? And they communicate between the members of the family by using the sound. And this ultrasonic sound is being produced by these whales, and I've also found that there are certain patterns in which they produce, which means they have some kind of a language. Say that, guys, I'm here. So they have some way of telling that using that sound, right? So interesting. We all humans think we are too great, too fun. We know language, we can speak, we can talk. We're too proud of ourselves. But the fact of the matter is, there are several other animals on this planet who are also extremely intelligent, and whales is another example, right? They have their own language. They have a notion of a society, a family, right, and all that stuff. So, and they're pretty intelligent, in fact, right? So let us not be too proud that we are humans and we are too great and the most wonderful thing which has happened to this planet. That's not true. There are a lot of other wonderful things here. All right? Okay. Fine. So sadly, I'm not able to show that. But what I want to tell you is that the whales communicate in sea or in oceans by using ultrasonic sound, right? Okay. Uh, okay. Now, if you've seen the speed of light, and you can see the speed of light is 300,000 kilometers per second, right? Whereas the speed of light, I'm sorry. The speed of light is 300,000 kilometers per second, whereas speed of sound is 300 meters per second. It's far, far, far less. It's like 1 by 10 crores times that of light, right? Yeah, lesser than that. So it's very, very small when compared to the speed of light. And that is why when a lightning happens, right? I would like to just quickly show you this video, right, of a lightning. I don't know whether I have copied it already. Yeah, I have. So you can see here. Sorry. This. And this you can observe yourself when there's a lightning happening, right? So you see the lightning first came and it took, okay, once again I'll show you. See? Did you see that? There was one lightning streak.
That.
Yes. Didn't you see? Sit nearby and see. See that? See how much time it took for the sound to come after the lightning. Right? Lightning happened, it took almost 2 seconds for the sound to come. So the reason why the difference is because the light is traveling at 300,000 kilometers per second, whereas the sound is traveling at 300 meters per second. So sound takes, even though all that light and the thunder in fact happened in the cloud at the same time, right? But because the light travels at a very high speed, you immediately see the light, but the sound takes longer time, right? Because it's happening a few kilometers away, high up on the sky is when it's happening. So it's taking longer time for it to come to your ears, and that's why you're hearing the sound later. Okay, I hope that's clear. So the one simple thing which you observe in the nature, the physics explains why that's happening that way. All right, now so we have seen that the sound is a mechanical wave and it needs a medium for transmission. But are we sure? If assume there's now light doesn't need a medium. Why? Because if you look at the light which is coming from the sun, there's a large part of the space between the sun and the earth which doesn't have anything. No gas, no liquid, no solid. Nothing is there. It is empty, or it's called a vacuum. It doesn't have any matter there. Still the light reaches us. So which means the light is not a mechanical wave. It doesn't require a medium. Whereas if you look at the sound, does it need a medium? Let us see. Right? Now we are going to look at this experiment, which is called a bell in a bell jar experiment, where you're keeping there's a bell jar. Inside the bell jar you're putting a bell, and then we are going to suck out all the air inside that bell jar, right? And then you're going to try to see whether the sound of the bell ringing reaches out. Right? Now let us try that. So you can see what is the arrangement here, right? So you have this bell jar. So this is the bell jar. And this is a bell inside. This is a bell inside, right? And this is a vacuum pump, right? So what the vacuum pump is, it's pulling out, sucking out all the air. So it sucks out all air, right? So that's what this vacuum pump is doing, sucking out all the air from the bell jar. Sorry for that. So it's sucking out all the air from the bell jar. So this vacuum pump is sucking out all the air from the bell jar. And let us see what happens. Will we be able to hear the bell, right? So I'm just going to clear this and I'm going to just run the video. So now you are able to hear it. Now he has started off the vacuum pump. This is slowly becoming reduced, because air is being pumped out more and more. Now there's hardly any air. Now you can see that after a while you not hear anything. See? Now it's gone. You're not hearing the bell ringing. The sound is because of the vacuum pump, right? So you can see initially you are hearing clearly. Initially you are clearly hearing the bell ringing. You're clearly hearing the bell ringing. Then once he switched on the vacuum pump and once all the air was pumped out of the bell jar, you're finding that you're hardly hearing the bell after that. So it's very clear. So what is really happening? See, inside the bell jar is a bell, and around the bell there's air, and when the bell is ringing, it is vibrating, and that vibrations are transmitted to the air, and those vibrations hits on the surface of the bell jar, and then the bell jar vibrates, right? And that vibration is coming out. When there is no air inside, what's happening? The bell is vibrating, but there is nothing which can carry that vibration out. Because why? Sound is a mechanical wave. It needs medium. If it doesn't have medium, there are no particles which it can make vibrate and transmit the sound. So there is no medium for the longitudinal wave to be transmitted, and because of that is why after a while you can see that you can hardly hear the bell ringing. I hope that's very clear. So this experiment very clearly proves that you need a medium for the sound to be transmitted.
Only the bell will be the motion of that
Bell you can see.
motion of the bell you can see.
Why you can see that? Because you're seeing that motion, because the light is hitting on the bell and that reflected light is coming to your eyes, and the light doesn't require a medium. So you are able to see. Very valid points. The student was pointing one thing. See, even though I'm not able to hear the sound, I can hear the bells vibrating. Why? Because you're seeing it because of light. And light doesn't require a medium. Because light is not a mechanical wave, it is a electromagnetic wave.
You can see it, but
You cannot hear it. Precisely. Okay? So I think that's very clear. I think you've understood that. Now, which means that the sound always requires a medium. It could be a solid, it could be a liquid, or it could be a gas, but it needs a medium. Without a medium, the sound cannot be transmitted, because sound is a mechanical wave and it's a longitudinal wave. It requires particles to vibrate, without which it cannot be transmitted. Alright. Now, the astronauts on moon communicate with each other using radio waves. That's very interesting, right? Now, why is that happening? Because moon hardly has atmosphere. Moon really doesn't have an atmosphere, right? Since the moon doesn't have an atmosphere, there's no medium. It's almost like, it's very, very thin. The atmosphere is very thin.
we hear each other.
So if I talk, hey Sidhu, the Sidhu will look at and see. That's all. Because there's no medium.
Even if I go near you also.
No, because there's no medium. There's no atmosphere.
Even if I'm this close to you.
Yes, even then. So what they do is, they actually have what you call, tell me. So they have got what you call walkie-talkies, right? So what they, and always the astronauts, when they are walking on the moon, they cannot simply walk like that. Why? Because the atmospheric pressure is almost negligible. And as well as when the atmospheric pressure becomes negligible, what happens? A lot of crazy things happen. Your blood will start boiling in moon, right? Because the blood is, your human body is tuned to live in a place, in a planet where there's atmospheric pressure. As soon as you go to some other place where there's no atmospheric pressure, your body goes for a toss. Why? Because your blood pressure inside the heart maintains that blood pressure at atmospheric temperature pressure.
Body burst.
Kind of something very weird will happen like that, right? And the blood will start boiling. Now, if you ask me why, we need to get into Pascal's law. I mean, you need to get into Charles' law and Boyle's law and all that stuff. So we'll look at that later, but you'll understand that later why that happens, right? And so because of that, they put what you call an astronaut suit, right? They put a suit,
And they put
and
something on.
yeah, and that suit inside maintains atmospheric pressure. So inside that, so you have a suit, inside the suit is the body, and that inside the suit they maintain atmospheric
And
pressure.
that is how they hear this.
No, that's not how they hear this. So because see, when he talks, the sound has to go out of the suit through the atmosphere and reach the other person. No, there's no atmosphere. So what will you do? So what they do is, they have got what you call inside they've got walkie-talkies. So they talk inside the suit. They talk, and that walkie-talkie will produce radio waves, which are electromagnetic waves, which is received by the other walkie-talkie which the other person has, and then that radio waves is converted to sound waves inside the suit, and then he is hearing. Inside the suit there is air. Understood? So that is what is happening. So between the two astronauts, the communication happening in radio waves because there's hardly any atmosphere in the moon. You understood? Is it clear?
Yeah, it's
So it's like this, right? So you have the astronaut suit. So this is the astronaut suit, right? And inside that there's an astronaut. Okay, it's very bad drawing, but still, right? I hope you get the idea. So this is the other astronaut, right? In fact, the shape of this is like a shape of a human, right? The suit. Now what happens is he talks. Inside there is air in atmospheric pressure. Right? So there's air in atmospheric pressure, same here also, right? When he talks, he has got what he call a walkie-talkie here, which receives the audio waves. Why it's able to reduce? Because the walkie-talkie is also inside the suit, and since there is air inside the suit, the sound waves can travel and it reaches the walkie-talkie, and from walkie-talkie it transmits as radio waves. So this is radio waves.
it looks somewhat like the echolocation. These kind of waves.
No, that is this is not the way the waves look like. I'm just representing it so that you can understand. Right? So radio waves, and now this walkie-talkie here receives the radio waves, receives it, and then the walkie-talkie converts the radio waves into audio waves, and since again there is air here, the audio waves can go to his ear and he hears. This is what's going on, right? So why we are using radio waves is because radio waves is electromagnetic wave. It doesn't require a medium. Does not require a medium. So this is the walkie-talkie. Okay, understood? Okay, fine. So now I think that is clear to you about the vacuum and why the medium is required, and that is how in Moon this is how they solve the problem by using radio waves, so that they are not dependent on a medium, right? And so I hope that's clear. Now I want to also talk about what is a sonar, right? So sonar is nothing but sound navigation and ranging. That is what sonar is. In fact, what the sonar is again based on the same principle of echolocation, right? So what is a sonar? So usually a sonar is used by ships to locate things under the sea, right? So here, for example, how does it do? It has got a transmitter which transmits a sound wave.
It hits that thing.
It hits the thing, comes back, and it looks at what is the delay, right? Now let us do some math here. So sound wave, so sound travels. So let us go back here. So here is a ship, okay, and it is traveling in it's going on water. Control C. I will just use blue here. and here is something down below, some rock maybe, right? So some rock here, okay. And now what it wants to do is it wants to find whether something is there and what is it, at what depth is it there, right? So what it does is it basically, it has got some transmitter here, right? And what a transmitter does is it transmits the sound wave, it transmits a sound wave, it goes here, right? And then it hits back. So it comes down and goes up. Now see, in water the velocity of sound is what? So velocity of sound in water is 1600 meter per second. That's the velocity of sound in water. So assume that the amount of time it took to go all the way here and come back is 2 seconds. So amount of time for sound signal to go and get reflected back, right? So as soon as it sends a signal, there's a timer. Timer checks, okay, the signal goes and it comes back. How much time it took for that? So assume for a sake of example, I'm saying assume this was, it took 1 second. So it took 1 second to go down and come back, right? So how much is the distance to travel in 1 second? So how much is the distance to travel? So it took 1 second to go all the way here and come back.
Speed into time.
Speed into time, absolutely. So distance, yeah, distance traveled. Brilliant. Distance traveled is 1600 into 1, which is 1600 meters. But it is to and fro, which means depth is this depth is see this going down and coming back is one depth plus one more. This is 2 depths.
Yeah.
So 2 depths is what is 1600. So the depth is, so 2, assume that this depth is d, right? This depth is d. So 2d is equal to 1600, right? So d is equal to 800. So the depth is 800 meters. So this is a very simple way of explaining, right, how the sonar is working. So this is what is really going on. It is somewhat like the same echolocation funda which bat uses or dolphins uses. The same concept, right? Now there are also more complicated things. See, what happens is that when the sound signal hits on the surface, some part of that sound signal is absorbed by the surface, right? So the strength of the signal which it receives back is lower than the strength of the signal which is transmitted. So it also looks at what is the reduction in strength, and based on that it will say what kind of material is this. Is it a rock? Is it soil? Is it mud? Right? Was it a fish? Was it, these kind of things it can say, because based on the surface on which it hits, the some portion of that signal is absorbed by the surface, and what this transmitter does is, okay, what is the weakening of the signal which has happened, and so it looks at the change in signal strength and based on that it can say what kind of surface did this wave hit. So that is the thing. So it can say what is the depth at which that thing is there, and can also say what kind of material was that. Okay, so this is basically what the basic principle of sonar is. Okay, and this is the basic principle. I will just okay, clear? All right. So that's basically about the sonar and how it works. And now let us look at some of the things. Using the sonar, how the ship scans the floor of a ocean, right? So it can start scanning the floor of the ocean, figure out what is there. See, you can see one of the sonar image. It shows about some boat which had capsized long time back, which is on the floor of the sea. And this sonar image has been created by the same echolocation principle, where it scans the bottom of the sea and can kind of see what is there on the sea. This is another example. This is actually, it is used for by these fishing ships. It kind of wants to know where the ship, so you can see that where the fish is located, and it finds there's some fish here, there's some fish here, right? And so based on that it knows which depth, which location is it, and then the ship can go there and can capture the fishes. So these are all principles which is the sonar using which it locates things under the ocean, and it also can scan the floor of the ocean and so on. Okay, so I think we kind of will summarize what we discussed till now. We did discuss about the characteristics of wave. We found that sound is a longitudinal wave, it's a mechanical wave. We looked at the pressure variation in sound and looked at the graph, and we defined what's a wavelength, amplitude, and the frequency. Then after that we looked at the medium, right? The sound requires medium for propagation. We looked at speed of sound in solid, liquid, and gas, and we found that solid has the highest speed, liquid has the next highest speed, and the gas has the least. And we found that the reason why that is because it's a mechanical wave, and because of sound the particles are thickly packed, and that is why it transmits far faster than liquid and gases, right? Then we also looked at experiment, the bell jar experiment. We proved that sound definitely requires medium for transmission, and then we also looked at the principle of sonar and how it works, right? Now with this we'll stop the session, and we'll continue tomorrow. The next session we'll discuss about how a human ear works. Okay, so I just want to let you know once again that this video is coming from Navayug Study, which is study channel. You can actually get in touch with us through this email, navayug.study@gmail.com. You can also visit our website, navayugstudy.wordpress.com, which has got links to all the videos and links to presentation material that I've used, everything. Have a great day. Have fun learning science. We'll come back to you later. Continue with sound in the next session. But till then, bye-bye.